is it recording? Yes. Great. Okay. Here we go. So today we're going to be discussing the metaphysics of the block universe, so the B theory of time. So the block universe view of time, of course, treats time in the same way that we treat space. It uses only the B theory, so it says only that events have a temporal order before and after. There is no objective moment now, so time doesn't actually pass in this view, and there's nothing special about the moment we call now. So this view, it contrasts very sharply against what Dainton calls the natural view of time, which is just based on a very naive, everyday experience of time that most people seem to, work with. And this natural view says that we have knowledge of the past and memories of our past experiences. We anticipate the future and we make decisions about what we will do. And we have this kind of vivid experience that we're only living in this brief moment now. So we have different attitudes towards the past, present, and future, which seem to be maybe in conflict. And we experience this temporal passage, which maybe also seems to be in conflict with this understanding of time presented by the block universe, where everything's just laid out, and there it is, atemporally. So if this is the case, some questions we need to ask then is that if there is no actual difference between past, present, and future kind of in the world, then how is it that we have time and change according to our own experiences? Why is it that we experience temporal passage? Or if you like, to get away from this idea of experience and consciousness, why is it that we still use the A theory of time? It seems indispensable that we still use the concepts of past, present, future, and the moment now, of course. So, can there be a satisfactory B theory account of time, or is fundamental temporal passage necessary for time, or at least our everyday conception of time? Do we still need the A theory? So today we'll start with questioning why we'd believe in this very abstract picture of time that stands so apart from experience. So we'll start with that. Actually, the main reason for believing it, I think, comes from best space-time theory. So I'm actually going to spend quite a bit of time just explaining what special relativity tells us about time. And then last week, a lot of people asked me about determinism. This picture of time seems quite deterministic. So I thought I'd spend just a couple of moments on this question. Not too much, though. We might have a later lecture if there's interest in determinism. And then for the rest of the lecture, I'll just follow some of what Dainton says. So how can these B theories account for change? Why do we have different attitudes towards the past, present, and future? Emergent time, I didn't get around to writing those slides, so we won't do emergent time. But I think in the discussion, you will do the emergent time. But we've already discussed this idea quite a bit already, about this idea whether if quantum gravity challenges our conception of time and maybe space and time don't exist in the theory, does that mean just because time isn't fundamental that it's not real? So these sorts of questions we'll discuss. And then some information about the first essay. And yeah, then we'll have a break and then the discussion. Cool. So, why believe in the block universe? So, I think there are three main motivations, or different lines of reasoning that could have you led to the block universe view. The first, and I think the most primary one, is motivations from our current space-time theories of physics. So yeah, I'll discuss a bit about what special relativity tells us about the nature of time. Also, we might question this natural view of time. You know, Dainton puts it forward like, yeah, everyone just has this natural view of time intuitively, but you know, maybe you don't, and why would you start from that? So that's another path that you might follow. Also, as we've seen, there might be problems or dissatisfaction with kind of the A picture of time. The idea that there is temporal passage might lead you into like Taggart-style paradoxes, or you might find that other accounts of time that use the A theory are quite unsatisfactory. So next week we'll be looking at some other ideas of time. And if you find those unsatisfactory, well then you might be led back to the block universe view. Okay. So today, I'll just focus on the first motivation and a bit on the second motivation. So, special relativity, developed by Einstein in 1905. It's a theory that applies to systems that move very, very fast, but not accelerating. So these are known as inertial systems. And it's based on two postulates. Firstly, the principle of relativity, and secondly, the constancy of the speed of light. And from these two, you get the whole theory. And what it tells us about time, in a nutshell, is that time is treated as a dimension of space-time. So it's put on the same footing as space. Also, it says that there is no universal moment now. That's the same throughout the universe. Also, it says that time passes differently for different observers. So all of these follow just from these two postulates. I'm not going to derive them though. So we're used to, hopefully, if we've got just two spatial dimensions, we represent it as a plane. So your x dimension, the y dimension, your x dimension, and then if you are a point on this plane located, you give coordinates, so x and y. We've seen when we add in an extra dimension of time here. So here you've got two dimensions of space and one dimension of time. In reality, of course, we've got three dimensions of space and one of time, but it's a bit harder to draw that. So now you're described by three coordinates, the two spatial and the one temporal. And the idea is each one of these slices represents your location in space-time at given temporal instances. So each slice is a temporal instant. And if you slice it all up and stick it all together, you end up with this picture of the block universe, and you've got your space-time worm or world line. So this represents your your position in space-time over the continuum of space and time. So that's the block picture. And again, you're led to this for the whole universe. Everything has a world line. And it's all laid out in this block. So the first postulate of special relativity holds that all the laws of physics are the same in any reference frame, so long as it's not accelerating. So if you are observer A and you're on the train, there's a system, there's a train moving with velocity v in this direction, and there's an observer on the platform looking at it. So if you're observer A and you're sitting in your train car, you're looking out and you're seeing observer B, and what you see is observer B moving away from you. So from your perspective, you're stationary, you're not moving. It's the rest of the world out there that's moving away from you. From your perspective, you can do any physics experiment you want. So they say things like you can have little birds fly around, you can bounce a ball, play around with water. Everything you do will behave like you're not moving, so long as you're going with a constant velocity. this guy's moving away from you with a constant velocity, say it that way. And similarly, this guy on the platform will see observer A and their reference frame moving away from them. And the same thing, any physics experiment you can conduct out here shows that you're not moving. So the laws of physics are going to be the same no matter what frame of reference you're in. Neither one of these would be privileged. I mean, it's not the best example because obviously there's a bigger frame here, which is the Earth, and this one's moving with respect to the Earth. So it's more natural to say that one's moving. But ignoring that fact, just treat them both as, two different frames that are moving with respect to one another. So postulate 2 says that the speed of light is constant and it takes the same value in all reference frames. So it's going to be the same if you're on the train than if you're on the platform. And that can be a bit surprising. So if the train, for instance, has a headlight with the light going out, and you're observer B on the platform, you might expect, well, light has its velocity c, and the train has its own velocity, so the light should have its own velocity plus the velocity of the train. But in fact, that's not the case. It just has the velocity c. So that's surprising too. So light, like all electromagnetic radiation, it travels with a finite speed. So it doesn't just instantaneously reach you. For instance, light from the sun takes 8 minutes to reach us here on Earth. If we were further away, then it would take longer to reach us. And this being the fastest speed, it's the fastest speed we can influence one another. So if you're on a planet over here and there's an alien on a faraway planet who wants to communicate with you, the alien turns on the light, but it will take some time for the light to reach you. So there's a time that takes for this causal influence to reach you. It's not instantaneous. So what this means is that at any given point in time and position in space, there's signals that can reach you and signals that can't reach you. As time goes on, by which I mean as you move forward in time to get away from this idea of flow, more signals can reach you. More distant signals have time to catch up with you. And similarly, the signals you send out can only reach a finite distance in a given time. So what this means is that any event, which is characterized by having a particular location in space and time, can only have been influenced by a finite number of other events. And these are events known as in its causal past. And it can only influence, in turn, a number of other events. And these are the events in its causal future. And together these define what's known as the light cone structure. So how we represent this, basically light waves, they radiate outward spherically. So imagine when you drop a stone into water and you see the ripples expanding out. It's basically like that, but this is obviously only a two-dimensional representation, and on the water it would be a two-dimensional. So imagine it spherically, light will radiate outwards from the event that's emitting the light. So representing this on a two-dimensional plane would be like this. But on a three-dimensional depiction like what I showed before, having the different slices of time, it would look like this. So you can see how these are light cones. So if you are this guy here at the origin of this coordinate system 0, 0, 0, everything that's located in this cone is able to have influenced you, because light signals that come from within here can get to you. If they're out here, they would have to go too fast before they can reach you. So these crosses represent the speed of light. Similarly, if you send out a signal, it would be along this cone, and you can influence things with that signal, and everything within it represents things that can travel from you under the speed of light. So this is your future light cone. It represents everything that you can influence. Okay. Is that clear? Good, good. Okay. So what does this all mean? Well, it actually implies that two observers will disagree on whether two events occurred at the same time, or whether one event occurred before another. And this is known as the relativity of simultaneity. Furthermore, because no observer's perspective is privileged, there's no fact of the matter whether the events occurred at the same time or not. So here's an example of this. Again, there's a train is moving in this direction with some velocity v, and there's an observer on the platform watching the train. Now imagine that lightning strikes both ends of the train from your perspective as observer B. You see both hit at the same time. But for this guy on the train, you'll actually see the green one as hitting the train before the yellow one. And again, because there's no privileged reference frame here, there's no fact of the matter whether one occurred before the other or not. So to see this, again, imagine, like I said before, light rays emanate out spherically. So after some time has passed and the train's moved forward a bit, the light signal from the green bolt has moved closer to the person on the train. So you see it first, whereas because you're moving away from the yellow one, it takes longer to reach you. So from this perspective, you see both as hitting at the same time, but from the perspective on the train, you see hitting at different times. Okay. Yes? Okay, good. So another surprising fact about special relativity and what it tells us about time is that it slows down depending on your state of motion relative to the signal. So two observers in relative motion will interpret time as running slower in the other observer's reference frame. And again, because no observer's perspective is privileged, there's no fact of the matter whether your clock is running slow or your friend's clock is running slow. This one's a bit more complicated. So you're on the train and you've got a very simple light clock, which is just two mirrors and a light signal bouncing between them, up and down. So each one would be a tick of the clock. From your perspective, you're not moving, and so your time's just ticking away like this. If that's 1 meter, then the light signal's traveling 1 meter up and 1 meter down. But from the perspective of someone on the platform watching you, you're the guy on the platform now. The clock on the train, by the time this signal is going back up, the mirror has moved because the train has moved. So the light has travelled a further distance than just 1 metre. You've got to do some trigonometry and work that out. It's travelled along the distance, and similarly to come back to complete the second tip. It's moved on already. So light's travelled along the distance here, but the speed is the same, then time has slowed down. You on the platform looking up at the train moving, you see that clock running slower than the one in front of you. So there was a little video. Oh, how do we get to the video? That's weird. Sorry, I should have queued this up before. Just so you can see it actually moving. Oh God.
Sjekk dem ut. Lego.com. Hemmelig kjæledyr i hvert sett. Settene selges hver for seg.
Obos-banken er laget for oss som Obos-medlemmer. Som medlem så får du tilgang til Obos-konto.
See why if we go back to Bob's train. Say Bob stands on the side of his train car that's closer to the platform, and he's facing a mirror on the opposite side of the car, 5 meters away. He shines a flashlight towards this mirror, which reflects the light right back towards him. From Bob's point of view on the train, the situation's very simple. The light travelled straight to the mirror and back, a distance of 10 meters, at the speed of light. Sure, looking through the window, you saw the light travel to the mirror and back, but meanwhile, the train was still moving. While the light travelled towards the mirror moved sideways relative to your spot on the platform. And while the light travelled back toward Bob, Bob moved even further sideways. The result is that you saw the light travel diagonally, as though its path formed two sides of a triangle. From your point of view, the light travelled a greater distance than it did from Bob's point of view. But special relativity tells us that the light's speed was exactly c, even though it travelled a greater distance. And if the light travelled a greater distance at the same speed, then it must have been travelling for longer. You and Bob are both timing the exact same series of events, but you're measuring a longer time than Bob is. So,
okay, so that was the video. I just couldn't find anything else that had that emotion. Alright, cool. Back to presenting. Cool. So, that's what special relativity tells us about time. That clocks will run slower depending on your state of motion. That time is treated as a dimension of space-time. And that, what was the other one? That there's no single moment now. That's the same throughout the universe. Okay. So this definitely contrasts very sharply with this natural view of time that Dainton presents. We experience space and time in different ways, even though, according to special relativity and general relativity, time is just another dimension of space-time and should be on more or less equal footing than space. It's actually not exactly the same as space because the metric you use, it's like this. So these being your three spatial dimensions and this being your time dimension, there is actually a negative sign here. So they're not treated on exactly the same footing. The negative sign is conventional. What matters is that there's a difference here in signs between the two. And that comes out from the theory. Okay, so we experience space and time in different ways. Even though according to this theory, they should be on the same footing. So Dainton says, well, maybe this is just due to our biology and what it is to be a human being, that we just, such that we perceive this. So the reason why might be that our perception of now is restricted only to a limited little window known as the species present. So it's not an instant, but it's not like the whole of time either. And estimates of it, which I'm not sure how scientific these are, between 3/4 of a second and 1.5 seconds. So how this works is that our brain creates a mental picture of what's happening now based on sensory inputs received at different times. So this is like a weird thing. So if you like bend over and touch your toe without having shoes on, you feel yourself touch the toe, and you see yourself touch the toe at the same time, but that light signal from the toe to your eye has gone quicker than the signal from your toe running through your nerves and then into your brain. And your brain takes these two inputs and puts them into the same event. So what you're perceiving at any moment is an interpretation that your mind has created based on different sensory inputs received at different times. And the species present itself kind of has a duration of its own as well. So when you listen to music, for instance, you don't just hear one note and then the next note. You hear music kind of in this range is the idea. This is the range where you can still kind of hear the last note that just played, and you can hear the note that's now playing, and then you also anticipate the next note that's coming in. So in this little window, you have all this experience. So this is a picture trying to represent this. If you have an event and it spans whatever this time is, and it gives you a stimulus, so has touching your senses between these two times. It takes extra moment for your brain to turn it into an experience, and then you perceive this. This would be your species present. Okay. So the suggestion is that all of this plus our memories that accumulate gives us this feeling of temporal passage, even if it's not actually in the world. Okay. So, very briefly on, well, I guess any questions on that? Maybe. Yeah?
You're talking about the experience of time going slower, but actually the light has the same, just has the speed of light, and the distance also is 1 meter, although it seems from outside that it's longer than 1 meter.
Exactly.
But we hear the stories about in science fiction about going very fast and coming back, and your twin brother is much older than you are.
Yeah.
So, and if that is correct, it is more than a kind of experience. It's actually a real time difference in a way, real in a way.
Yeah. So exactly. In that effect, the symmetry has been broken. Yeah, it's no longer that your clock's running slow to their clock. Sorry, their clock's running slow to your clock, and your clock's running slow compared to their clock. In that instance, one clock has actually gone slower than the other, and that would require breaking the symmetry between the two. So there's different ways of resolving this, but in that case, it's due to the fact, well, the explanation that's usually given, even though it's a bit more complicated, is that special relativity doesn't apply when you're slowing down. So you're on the rocket ship, you have to slow down to turn around and come back. And that's de-acceleration and then a re-acceleration. Whereas the theory is only symmetric for non-accelerating systems. But I think later on we'll have a session on special relativity and we can discuss more about it. Yeah, it's a good question. Alright, so very briefly on determinism, because it came up a bit last week. Special and general relativity are deterministic theories in one sense. This means that given the complete state of the universe at any one time, we can compute the state of the universe at any other time, whether this is a time, a greater time or a smaller time. You can take this input state, put it into the theories, and run it through, and you'll end up with the state at any other time. So this block universe picture of time also appears deterministic. So everything that has happened or will happen, it's all just laid out there. So like the death of Queen Anne that we were discussing last week, it always will be the fact that you are going to be sitting right here in this classroom listening to me talk at 12:47 on the 3rd of February 2020. But does this mean you have no free will? Well, it's a big question. What do you mean by free will? And does it have to be tied to our scientific theories in this way? There are pictures that, compatibilism, which says that free will can be compatible with this. There's incompatibilism, which says that free will isn't compatible with this. So there's lots of different responses you can take to this question. And I'm not an expert, but if you're interested, we could do more of this in the future classes. The only point that I wanted to make today was that if you really want to tie these sort of questions to physics, is that special and general relativity aren't our only theories of physics. We also have quantum mechanics, which is an indeterministic theory in some sense. The sense is that it doesn't give deterministic predictions. Given a state that you input into the theory, all you can get out is a probability that the system's going to be in a particular state at a particular time afterward. Additionally, the theory says that we can't know the complete state of a system to arbitrarily high degree. This is because of the Heisenberg uncertainty relations. So it stops us from even having the complete state in order to put into these deterministic equations of GR, for instance. But the question is whether this represents a fundamental indeterminacy or whether it's just due to the interpretation. So there are some interpretations of quantum mechanics that say, yeah, it's a fundamental indeterminacy, being nature's random at the most basic level. And people do, a lot of physicists I've talked to as well, they're really into this because, this is the opening for free will that we need, and they tie it to this. But other interpretations, hidden variable interpretations, say no, quantum states actually do have definite, they can be completely definite. And this is just, our description of them is inadequate in some way. So there's a lot more to be said on this, and this was just kind of give you some little taste of the sort of issues that are out there. All right. So to finish up, I'll look briefly at the B theories of change. So if all time is timelessly laid out in a block, the block itself doesn't change, but an object within the universe changes according to the B theory, like we saw last week, by having different properties at different times. So you have two statements. One, the poker is hot at time t1. Two, the poker is cold at time t2. These facts are changeless, they're just out there, but they describe a change in the object because it's possessing different properties at different times. Now, there are two further metaphysical views on how this is possible, revisionary and non-revisionary. And for this, I've taken it straight out of the book. What did I say? 3.7 is the reference to Dainton for this. So the revisionary account revisionary means you go back and revise some of your conceptual system. In this case, you need to reconceive what you understand as persisting objects. On this account, we treat objects as having temporal parts as well as spatial parts. So a spatial part would be my hand, my arm, my head. They're parts of me that are located in different parts of space. If I give my head an XY coordinate, give my arm an XY coordinate, they're going to be different. But the idea is that objects also have temporal parts. So at each moment, each t coordinate here represents a different temporal part in exactly the same way. So each slice represents a different temporal part of your friend Alice. So if you're down here and you see Alice at T1, you're not seeing the entirety of Alice, you're just seeing the temporal part of Alice that's located at T1. So all these temporal parts are parts of the one object, being Alice. And they're all equally real, just as all times are equally real according to the block universe picture. But they can differ from one another, of course. You've got different spatiotemporal coordinates. And the differences between them represents change, is the idea on this account. So change is temporal variation, analogous to spatial variation. The alternative picture to this is the non-revisionary account, which is advocated by Hugh Mellor. If you think, this idea of temporal parts is just super weird, and when you see someone, you're seeing the whole person, not just a temporal part of the person, then you might like this metaphysical view, where we keep our usual understanding of objects as existing in their entirety at any given moment. So this relies on a distinction between objects and events. Objects have spatial parts, my hand, my arm, my head, but you have to treat these parts as different entities. So my hand is a different part of me than my head. They're distinct entities. He says that objects don't have temporal parts. You just have a single entity persisting throughout all times. And this, has a different idea of change. Change is possible by virtue of this one entity having different properties at different times. So change is distinct from spatial variation. Spatial variation would be moving the different, this is where it gets weird, different, I'm varying from my arm, which is a distinct entity from my head, but that's not a change because they're two different things. Even though they're spatially located at different places, that's not a change. Change can only occur for a single entity. So it's important that an object is just a single entity throughout time, and it's thanks to this object having different properties at different times that you get change. On this view too, events have different temporal parts, but objects don't. And events, he says, don't change. They just occur at the time, and that's it. The next event, it doesn't represent a change because it's just two different entities. Okay. So, in the last 5 minutes, maybe I'll do a little bit on this, the first question of attitude, and then briefly on assignment 1. So, if the past, present, and future all have equal status, then why do we have different attitudes to these experiences? why are we more concerned with future pleasure and pain than we are with our past experiences of pleasure and pain? Just according to Dainton and the literature, huge literature on this. But I already wonder, like, is this true? No. I kind of would, like, if I could go back and change a painful experience, I feel like you would anyway, wouldn't you? But anyway. So I think this is debatable. Also, a question that gets debated a lot in the literature is, why do we care more about immediate future pain than about distant future pain? If it's all laid out and going to happen anyway, why do we have these different attitudes? And also, we won't have time to discuss this one until after the break, but why does this differ when we're considering our own experiences compared with the experiences of others? So this is Arthur Pryor thinks that we can't make sense of this without reference to the A theory, without having an idea of now. He says, half the time, personally, I've forgotten what date it is, like a typical philosopher. I have to look it up or ask somebody when I need it. Yet, I still manage to communicate and make myself one understood without having to resort to this B theory of time. You can say, thank goodness that's over. And not only is this, when said, quite clear without having a date, it says something which is impossible to convey without, if you were to just use the B theory of time. It doesn't mean the same as, thank goodness the date of the conclusion of that thing is whatever the date is, nor does it mean, thank goodness the conclusion of that thing is when I say it. Why should anyone thank goodness for that? So this is a number of problems gone into this. So imagine you've just come out of the dentist and it was very painful, and you say, "Oh, thank God that's over." But what are you thankful for? The B theory has a challenge. The A theorists can say quite straightforwardly, "I'm thankful for the fact that my dentist visit is now past. It's no longer happening to me." Whereas the B theorists can't say that. There is no fact that your dentist visit is now past. All you can say is that, thank goodness that that event was before me being at this event. So from the point of view of the B theory, if all events always occur in this order, then it was always the case that your dentist visit was going to be over at noon on the date that it happened, you know. So another, I didn't put it in the other, oh yeah. So there's two questions you need to ask. You need to explain, what are we being thankful for when we say it? And we need to explain why it's only appropriate to say it after the dentist visit, rather before or during the dentist visit. Because it was always the case that you leaving the dentist visit was going to happen after the dentist visit. This was the case even before the dentist visit, before you had even booked it in. And yet you only say, thank goodness that's over, after. So these are two challenges. Alright, so skip these ones. And just finally on the essay, so these are two suggested topics. Firstly, can the Block University be defended against the concerns of the A theorists that there's no change in the world and that time passes, so what we've just been discussing? Or you can write about McTaggart's argument. Does it show that time's unreal? Or if you don't like these topics or have something else in mind that you're more interested in writing on, so long that it's about time and related to things in the first part of this course. So if you want to write something about time travel, time asymmetry, that's fine. Just come and discuss it with me before you start writing it. We'll agree on a topic. Okay, so that will be 5 to 6 pages is the idea. I meant to ask you, because the administrator's away, does that mean double spaced? What's typical Yeah, I know, 5 or 6 double space. No?
1.5.
1.5. Okay, cool.
And Times New Roman 12 point.
Thank you. Times New Roman 12 point, 1.5 space. Alright, cool. So we'll have a break now, and afterwards we'll start with the discussion. Thanks.